So let's assume Z as set of instrument. Okay, set of instrument, and assume that there are capital L number of instruments in set. Okay. Now there can be two cases. So case 1, L is equals to K, and case 2 is L is greater than equals to K. What is K? K is basically total number of parameters to be estimated in the model. Okay, total number of parameters. That means if we go back to our original equation, let's say here in beta consists of K number of parameters including the intercept. So I have K number of parameters to be estimated, but I have L number of instruments within this Z instrument matrix, and then L can be either equals to K number of parameters to be estimated, or L can be greater than or equals to K. Okay. Now the population moment condition, once again, when you have Z, the population moment condition when you are estimating this equation with IV approach, what would be my population moment condition? Expectation Zi Ui equals to 0, and then the IV estimation, basically the IV estimation, let's say this is equation, let's say this is equation 1, then this is equation 2, subsequently this is equation 3, and then let's say this is equation 4. So the IV estimation, okay, the IV estimation solves the sample moment, counterpart, sample moment condition counterpart of equation 4, which is basically the population moment condition. So what would be the sample moment condition? Previously we saw that, if you go back, we saw that if this is my population moment condition, what is my sample moment condition? 1 by n summation xi into yi minus xi beta hat. Same thing we will do it here, 1 by n summation zi prime into yi minus xi into beta tilde where beta tilde is basically the IV estimates. Okay, beta tilde is the IV estimates that we are assuming, that equals to 0. Let us say this is equation 5. And if we assume case 1, if we assume case 1, that means L equals to K, then this beta tilde equals to Z prime X inverse Z prime Y. Okay. So now again we have derived the IV estimators using this moment condition. Okay, beta tilde equals to Z prime X inverse Z prime Y. So this is fine. That means as long as my number of instruments are equals to number of parameters to be estimated from the model, I am fine. That means my IV estimation also looks like the OLS estimate what we have derived earlier. In place of X prime X inverse X prime Y, this is like Z prime X inverse Z prime Y. So Z is basically set of instruments. So we have substituted X with Z, that's all. Okay. So that means in case of exactly identified system, my method of moment estimation in presence of endogeneity, or that means my IV estimates we can derive by using the sample moment condition, which looks like beta tilde equals to Z prime X inverse Z prime Y. Now the case becomes complicated when we assume, now let us assume that L is actually greater than K. Okay, that means we have more number of instruments than the number of parameters to be estimated. Okay, more number of instruments than the number of parameters to be estimated. That means more equations, and each instrument will give rise to each one sample moment condition like this. 1 by n sum of Z prime X inverse, this is basically Z prime multiplied by Z transpose into yi minus xi beta tilde. So here I have assumed that number of equations are actually equals to the number of instruments are basically equals to number of parameters to be estimated. Then the moment we get more instruments than number of parameters to be estimated, then what will happen? That will lead to a situation more equations than number of unknown parameter. number of unknown parameters. Okay. So, what we can do in this case, inefficient solution is when you have more instruments than number of parameters to be estimated, then we can always select k number of instruments out of the set of L instruments. Okay, L is greater than k, so what I can do, I will take only k number of instruments from the set of L, and that will lead to an inefficient solution. Okay, inefficient solution. Now here comes GMM. What is that? But instead of doing this, instead of selecting k instruments from L, what we can do, we can do the following. Okay, we can do the following, that is more efficient actually. Okay, and that is the GMM estimator, which is nothing but what we actually doing. I will write it here, Qn, and then beta means beta GMM equals to 1 by n, then Zi prime yi minus xi prime beta. Okay, we will take, see, this is the sample moment condition which we have derived earlier. We will use that, take transpose of that, and then we will use one W weight matrix, and then we will multiply this 1 by n sum of Zi prime yi minus xi beta. Okay, so we will minimize this. So this is called quadratic loss function. Okay, so I will select the beta. So what the idea here is, the Wn is basically L by L weight matrix, L by L matrix of weights that chosen optimally that gives smallest variance GMM estimate. So that means what I am actually doing, when L is greater than K, instead of selecting K number of instrument out of L, I can construct a quadratic loss function, that means minimizing this particular equation, which is derived from the sample moment condition 1 by n sum of Zi transpose into Yi minus Xi prime beta whole transpose multiplied by a weight matrix and then 1 by n Zi prime this. Okay. So that is the idea when I have more number of instruments than the parameters to be estimated, and that is basically, if you solve this, if you minimize this with respect to beta, then the solution will give you, the solution is basically beta hat GMM or beta tilde GMM, you can write, equals to summation Xi transpose Zi into W, then summation Zi transpose X, Xi transpose Zi into W, and then multiplied by Zi transpose X, and then you take whole inverse of this and then multiply with summation Xi transpose Zi into W multiplied by summation Zi transpose X, sorry, Zi transpose, this is Y, Xi transpose Zi W, Zi transpose Y. That will become your GMM estimates, which is derived from this particular quadratic loss function, which is again constructed by the sample moment condition, and that will lead to your beta hat GMM, beta tilde GMM, which is nothing but X transpose Z into W Z transpose X inverse X transpose Z W Z transpose Y. So this is basically your GMM estimates that we are talking about, and this is the GMM estimates that Arellano and Bond basically derived from this quadratic loss function. Okay, this is basically the idea of method of moment, and GMM is a generalized version of method of moment when your number of instruments are actually more than number of parameters to be estimated. And what is the method of moment condition? Method of moment condition is actually very simple if you go back, which is derived from the idea that no explanatory variable should be correlated with my error term. And if that is the case, I can use that expectation Xi Ui equals to 0, and if you replace u with the value, then you will get a population moment condition given by equation 2. From there, you just try to derive the sample moment condition, which is 1 by n summation Xi prime into Yi prime minus Xi prime beta hat, and then your beta hat is exactly X prime X inverse X prime Y. With this, I can show that OLS is basically a moment estimation. Okay. So OLS as a method of moment estimation we can prove by using this estimation. Okay. Now, if we relax that assumption, if we say that some of the explanatory variables are actually correlated with your error term, then what happens? You lose the consistency property. That means probability limit n tends to infinity, beta hat minus beta less than delta, which is equals to 1 minus epsilon, that is no longer true. This is the consistency property, right? So when that is the case, that means when you have endogeneity issues in the model, what we need to do? We need to identify instruments that are highly correlated with your endogenous variable but not at all correlated with the error term. Let us assume that Z as a set of instrument, okay, and we can assume two cases. Let us say that Z consists of L number of instruments. In first case, we assume L equals to K, where K is number of parameters to be estimated from the model. Now, if K is less than L, that means if you have more instruments than number of parameters to be estimated, then we can get a case of GMM. So, first we have derived L equals to K, again using the expectation condition. What is the expectation? That Zi Ui equals to 0. Instrument is not at all correlated with the error term. Then again I replace U by Yi minus x prime beta tilde, and then by solving this we will again get Z prime x inverse Z prime y when L equals to K, exactly same OLS estimates that we have derived earlier. In place of x we have written Z, that's all. But the situation gets complicated when L is actually greater than K, and we cannot select only K number of instruments out of that L, because that will lead to inefficient solution. Okay, to get an efficient solution, what we can do? We can actually construct a quadratic function in this way, where I am giving a weight, I am multiplying the sample moment condition, its transpose with a weight Wn, where W is basically L by L matrix of weight chosen optimally that gives smallest variance GMM. And then ultimately we will arrive at a solution where beta hat GMM equals to x prime z w z prime x inverse x prime z w z prime y. So that means you see in between I have z w z prime, z w z prime. That means that instrument and that this weight matrix is playing a role to finally get you the GMM estimation in a case where number of parameters are less than number of instruments. Now, why this is the case? Again, if you go back to our instrument matrix that we have derived in case of Arellano and Bourne's model, look at here what Arellano and Bourne suggested, that we should use all the information available in the system. We should use all types of all the moment conditions available in the system. That is why he suggested you include all the lags available for each period. So, yi t minus 2, that is coming based on the idea of Holz-Jackin. They also suggested the same thing, that second period lag. But additionally, and Arellano and Bourne said, apart from yi t minus 2, you see whatever lag is available for the untransformed variable. So, for endogenous variable only yi t minus 2 and above. For predetermined variable, it is basically your lag 1 is also available. So, if you include that, then you see the number of instrument is 1 for second period, now 2 for third period, 3 for the fourth period, and so on. So, you have enormous number of instruments. It is a over identifying system, and in that case we discussed about method of moments. And since this is a method of moment applied in a context where number of instruments are more than number of parameters to be estimated, that is called generalized method of moment. That's all. Okay, generalized method of moment. This is the idea of the Arellano-Bourne's method of GMM. We discussed little bit of theory of GMM also, so that it can give you a better picture, better understanding of the Arellano-Bourne model which we will estimation, and which I will show you in our next class about the proper estimation of this AB model using a sample data set. Okay. So far then what we have discussed is we introduce a dynamic panel data model using a single left hand side variable which is dynamic in nature, and then we have also discussed how that particular model leads to persistence over a period of time because of two factors, which is AI, unobserved effect, and also the lag dependent variable which basically introduces the autocorrelation in the model. And we proved that neither first difference nor fixed effect transformation is applicable the moment we apply these two methods to eliminate the unobserved effect from the model. Yes, we eliminate AI, but at the same time we get a problem which is called biased estimation and inconsistent estimation, because in both the cases, in fixed effect transformation as well as first difference transformation, we saw that my explanatory variable is still correlated with the error term, even though error term they themselves are serially uncorrelated. And then we discuss that if that is the case, instead of using OLS in the transform model, what you can do when in your first difference equation, you just use instrument for that difference variable which is getting correlated with the error term. And then we discussed about three basically approaches, started with Anderson and Hsieh, who said that we can use either second period lag or third period lag, but the condition is that if we use more lag, then your sample length will go down, because in each period, for each panel, you will lose observations, either one or two, depending on how many lags you are introducing. So to get rid of that problem, there is a sample trade-off between sample length and lag length. So to get rid of that problem, Holjakin et al., he said that instead of using too many lags, we will use only second period lag for each time period, and we will replace all the missing observation with 0, and in that way we will maintain sample length. But if we follow that approach, what is the problem? The problem is we will end up with having only second period lag. That means we are not using all the moment conditions available in the system. Then Arellano and Bond said we can increase the efficiency of this estimate tremendously if we use all the moment conditions available. How to do it? All the orthogonality condition or all the moment conditions available in the system? He suggested that you include all the lags available for the untransformed variable. That means yit minus 2, that is based on the IV style, and then you have other lags available, that is basically the GMM style. So two types of instruments are included here. So for second period, I have number of observation 1, from third period 2, fourth period 3. So as the number of period increases, we have so many number of instruments. It's an over identified system, and in that context we introduce GMM, generalized method of moment condition. Okay, when number of instruments are actually more than number of parameters to be estimated. Then what we will do in our next class, we will take a data set and we will try to understand. So far theoretically we have estimated, we have proved that neither first difference, we can neither use OLS not fixed effect model to estimate a situation which is dynamic in nature, because those things would be, that will give you biased estimates. We will show you what is the nature of the bias when we apply OLS in a dynamic panel data model, what is the nature of bias when we are applying fixed effect in that first difference in the dynamic panel data model. Okay, we will take a dynamic panel data model and we will apply OLS and fixed effect transformation First of all, to understand the bias, the magnitude of bias, and then we will uh, uh, go to our next models, this Arellano-Bonds model, to overcome that biasness. Okay, so that is basically about what we have discussed in our today's class. So with this, we are closing our discussion today, and in our next class, we will show the hands-on experience empirical estimation of this dynamic panel data model. So far we are using, please keep in mind that only the second leg of the untransformed variable. Okay, second leg of the untransformed variable. That is what we are discussing over here. But additionally, we can also take the second leg of the difference variable delta yit minus 2. And one more important thing before I forget, I need to mention over here at the end that in this system, all the instruments, please keep in mind that in Arellano-Bonds method, since we are using instruments for endogenous variable, lag of endogenous variable, lag of predetermined variable. So, in AB's approach, all the instruments are coming from within the system. Since instruments are formed from lag of endogenous and predetermined variable in the model. So previously when we discussed about IV estimation, if you recall, we were searching instruments from outside. If you recall, in the context of IV, we were discussing about estimating wage function. Wage is a function of your experience, education, and education we discussed that endogenous variable. We were trying to replace education with father's education and mother's education, which was not there in the system, which was not there in the model. So this father's education or mother's education they were coming from outside the model to act as instrument. But here is a case yit equals to yit minus 1 plus xit. My all instruments are coming either lag of this yit minus 1 or lag of any of the predetermined variable or exogenous variables, right? So that means this is a case of instruments coming from within the system. Okay, one advantage of this is that, as you know, the instrument requires two conditions to be satisfied. First of all, they should be highly correlated with the endogenous variable. Obviously, since instruments are coming from within the system, my yit minus 2 would definitely be correlated with yit minus 1 minus yit minus 2. But when you have too many instruments, then satisfying over-identifying restrictions for each of these instruments becomes a challenge for you. Okay? Unlike the other case when the instruments were coming from outside the system, satisfying the condition that the instruments are related with the endogenous variable but not with the error term, that it's a challenge. Here at least we can ensure that they are highly correlated, but they are too many in number, and then we need to satisfy the over identifying restrictions for each of these instruments. Okay, so with this we are closing our discussion today, and next day we will try to estimate an empirical model which is dynamic panel in nature, to understand what is the bias when you apply Wallace, what is the bias when you apply fixed epoch transformation, and how dynamic panel data approach can actually overcome that bias. Thank you.